In this section, we're going to look at functions and surfaces. Now we're going to start by actually studying a surface that we've already studied in the previous section. Oops, sorry, hit the wrong button there. Which is a plane, right? So if we have an equation of the form ax plus by plus cz plus d equals 0, where a, b, c, and d are all constant numbers, what we could do is we could solve for z. And so if we do solve for z, what we notice is that z is determined by both x and y. Okay. Now that idea of z being determined by other variables should make us think of functions in just functions of a single variable that we're already used to, right? So like if I say something like f of x is equal to x squared plus 1, what I really mean is that y is equal to x squared plus 1, right? That in order to figure out what the y value is, you take the x, square it, and add 1 to it, and that gives you your y. And so we understand that y really and f of x are really the same thing, right? F of x is just the function notation for this formula. And so similarly, now that we're working with three variables, x, y, and z, we're going to say that z can be a function of x and y. All right, so here's our formal definition for it, right? A function of two variables is a rule that assigns to each ordered pair of real numbers a unique real number denoted by f of x, y. We call that set of ordered pairs the domain, and then the range is just the set of all z values that you can take on. And this definition basically is just saying that this function is the z value, right, is what we're saying here. So it's the graph of f is the set of all points x, y, z, so that z equals f of x, y. Now, in order to really understand what's happening here, let's again go back to functions of just a single variable. Let me use a different one. So how about something like g of x is equal to the square root of x minus 1. So if I was to sketch a quick graph of that, I would know that the domain of this function is everything from 1 onward. And that after 1, the graph looks like this. Now, what we understand is that when we say that the domain is all numbers bigger than 1, you can kind of think of the domain as just this interval here, right, that goes on forever. And what happens is that you take each member of this domain and send it up to a y value. Okay, so just as for instance here, if you take the value 5, it gets sent up to the y value of 2. Okay, so this visual of taking the domain, which is just a bunch of x values, and sending them up to the y value is useful for us. But now what's going to happen is our domain is a set of ordered pairs. So now our domain isn't just an interval, it's this entire region right here. It's a bunch of ordered pairs. And, and it might have an interesting shape, or it might just be all ordered pairs. But the point is this is my domain, then I take members of that domain, just like I took this member 5 and sent it up to 2, I take members of this domain and send it up to its z value. And so just to kind of give a little bit more of a dynamic look at this, right, same kind of picture as you see in the notes there, but you can kind of rotate around. And so this is the surface up here. So the purple is the function values, right? That's the set of x, y, z ordered triples that form the surface. But what's happening is we're taking x, y values and sending them up to a particular z value. All right, so let's take a look at a concrete example here. So it asks us to find the domain of this function, the square root of 9 minus x squared minus y squared. Now, when you work with domains in earlier courses where you just have functions of one variable, you know that when you see square roots, you got to say that whatever's inside of them has to be greater than or equal to 0. It's no different here. So we still have to say 9 minus x squared minus y squared is greater than or equal to 0. But of course, I can, move stuff around here and add x squared and y squared to both sides. So I end up with this. X squared plus y squared is less than or equal to 9. Or if I flip it around, it might be easier to read. Okay. So what we're saying is that the domain is all x, y, so that x squared plus y squared is less than or equal to 9. Okay, so, well, what is this? Well, we did a little bit of work with inequalities at the very beginning of the chapter. But remember that x squared plus y squared equals 9. If I took away the less than or equal to, that is a circle, right? Circle of radius 3. All right, so over here, let's go ahead and sketch this like it asks us to. Make some axes here. All right, so I'm going to go 3 in every direction. All right, and so of course I'm going to go ahead and draw my circle. Let's do it in a different color here. So probably won't do a great job, but as I'm drawing this, I don't know if you can hear that or not, but sorry, my kids are playing very loudly outside. At least I hope they're playing. All right, so there's my circle. But it wasn't just the circle, right? It said less than or equal to. So it's like saying, okay, we need x squared plus y squared to be less than or equal to 9. So it's not just the circle, but I would in fact want to fill in the whole thing, right? So this is my domain. So what I want us to understand is that the domain of f of x, y is a region in the xy plane. So in other words, you can graph just using regular, two-dimensional techniques, your domain, right? And so in other words, this green circle that I've just made, that's like this tan region that's down here, right? And then sitting up above that region is the surface itself. Okay, now I would show a graph of this right now using technology, a graph of the function, but we're actually going to save that for later. But we'll come back to this idea and make sure that we were accurate with it. But what we just graphed is just the domain. All right, so here's one, and we will look at the graph of, we will look at a graph using technology of this one. So I have g of xy equals the natural log of y minus x cubed. So what do we know about natural log? We know that the argument, whatever's inside, can't be 0 or negative. In other words, it has to be greater than 0. So that means that y must be greater than x cubed. Okay, so let's see if we can make sense of that. So if I sketch this, all right, here's my x, here's my y. All right, so first of all, y equals x cubed. What does that look like? y equals x cubed, right, is just, this sort of thing, right? So what I want to do is graph here, but notice that I am not including that. So I'm going to be careful here, and as I graph it, I'm going to use a dashed line. So I'm going to go, 1, 1, -1, -1, because I know those are points, and 0, 0. Those are points that it goes through. And oops. And what I'm going to do is I am not going to graph this as a solid line. I'm going to graph it as a dashed line. So just like if I were to be working with a domain and I was writing the interval notation for my domain down and I didn't want to include an endpoint, I would put an open circle. The same idea for us would be that we use a dashed line on the curve instead of a solid line whenever we have just a strict inequality. All right, but then where do I shade? Well, we want y values greater than x cubed, or y values greater than this curve. So I'm going to shade in all the y's that are greater. So this shaded region here is my domain. Everything over here is not in the domain. Okay, but again, this is not a picture of the surface itself. This is a picture of its domain, or maybe another way of saying it would be the shadow that it casts on the xy plane. Now to see how that really all plays together, let me go ahead and show that. So what I'm going to do here is I'm going to go ahead and graph that function. So the natural log of y minus x cubed. Okay. Now at first this might look a little funky, but when we're using this thing, one thing you can always do is mess with the discretization, and that'll basically notice how big these rectangles are right now. So if I change these to 100, then it graphs it provides more pixels and so gives a greater accuracy. So we did 100 there, and that's probably enough. So here's what we're going to do. Let's align this. Okay, so first of all, this is kind of an interesting graph. It's, I wouldn't want to be walking along this ridge. It seems like I could slide down really easily. Okay, now these kind of drips of paint, as it seems they are, those aren't real features of the graph. That is just the computer. As we graph here, it's getting close to the edge of its domain, and so it's not going to fill in every little pixel here, and so that's not an actual feature of the graph. But here's the interesting part that I want to focus on. Let's line this up like a true XY plane. So you can see here the y's are going from -4 to 4, the x is from -4 to 4. So I want that -4, -4 in my lower left corner. So I'm going to have this thing rotate. There we go. Have this thing rotate so that I'm looking at it with increasing x and increasing y. So x is getting bigger here, y is getting bigger here. And what do you see? You see the y equals x cubed graph. And if you don't like those little ridges there, you can just increase further your discretization, and so then it's even a little smoother. Maybe I go up to 200, and look at that, that's even better. So hopefully kind of getting an idea of this idea of, okay, if I look straight down on the XY plane, this is the region where the surface exists. This is the region where it doesn't exist, right? Going back here, that's what I graphed in that spot right there. All right, and that's what's happening. And then here's my just a different view of that function. All right, so now let's look at example 3. Example 3 would be a good one for you to do on your own because you've actually done this already. All right, so I'd pause the video here and go ahead and sketch this function the best you can, trying to be as accurate as possible. All right, so when you went to sketch this, what I hope you kind of recalled from before is that when we are sketching planes, it's really nice to uh, be very accurate at the x, y, and z intercepts. So let's go ahead and find our x, y, and z intercepts. So first of all, let's do x-intercept. So that's when y equals z equals 0. So that's going to be, and just don't forget, right, this is your z, right? So that means we have 0 equals 2x plus 3/2 times 0 minus 6. So 0 equals 2x minus 6. So x is equal to 3. So I'm going to come over here, 1, 2, 3. Put a dot right there. And then my y-intercept, right? That's when z equals x equals 0. So 0 equals 2 times 0 plus 3/2 y minus 6. So 6 equals 3/2 y. And then 2/3 times 6 equals y, which is just going to be 4. Y equals 4. So 1, 2, 3, 4. So there's another point. And then finally my z-intercept, that's when x equals y equals 0. But that's just going to be z equals -6. So down 1, 2, 3, 4, 5, 6. And so what's really nice to do here is just to form a triangle with all of these, with the understanding that our plane goes on forever in all directions, but I can kind of get a good sense of what this plane actually looks like by connecting up those intercepts. Now, if you really wanted to, one thing you could do is you could kind of try to stay parallel to this line right here, and then also stay parallel to that original line, and then you kind of make more of a parallelogram out of it, and so you can certainly do that as well, but definitely at least have this triangle graphing or being asked to graph a plane. All right, so now we're going to return to example 1. So remember, here was example 1 where we found the domain, and so the domain was just this circle and everything inside of it. So now I want to make a full sketch of this graph. Now, the technique we're going to use is what's called sketching traces or cross sections, okay, of our graph. So in other words, we're going to use our two-dimensional graphing skills to help us along the way to sketching the full graph. All right, so we've actually already got one of these done. The domain of our function actually tells us exactly what the graph or what the edge of the graph happens to look like in the xy plane. And so while traces can be any cross section you want of your three-dimensional surface, a good place to start is to sketch the graph in the xz plane, the yz plane, and the xy plane. So we're going to start with the xy plane. We're going to sketch in xy plane. And what do we know about the xy plane? In the xy plane, z equals 0. All right, so we have 0 equals the square root of 9 minus x squared minus y squared. We, of course, can square both sides, right? That's no big deal. And so we get 0 equals 9 minus x squared minus y squared. And if I move the x and y squareds to the left side, I get x squared plus y squared equals 9. Well, that's just a circle, right? Which is exactly what we graphed back here. We graphed the circle of radius 3. So the sketch in the xy plane is just the circle of radius 3. So I'm going to go 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. And I think I want to space these out a little better. 1, 2, 3. There we go. All right, so circle of radius 3, these are the places that I need to be crossing, right? So then, of course, since I know I'm making a circle, I'm going to try my best to make it look like a circle in these places. All right. So what I've just done is I've graphed what the graph looks like if I was to slice away everything else and just look at the xy plane. Okay, so now what we're going to do is we're going to sketch a different plane. Let's sketch the YZ plane. YZ plane. In the YZ plane, x equals 0. So that means that we have z equals the square root of 9 minus 0 squared minus y squared. So that means z squared, if I square both sides, gives me 9 minus y squared. And then adding y squared to both sides gives me z squared plus y squared equals 9. But guess what? This is also a circle of radius 3, but let's be careful, but only the upper half. And why is it only the upper half? Because back here, z was equal to the positive square root. So z is always greater than or equal to 0. So as I go to sketch this, it's going to be a circle of radius 3, but only the upper half of that circle. So I'm going to go up 3. Okay, so there's up 3. Actually, let's make that a little bit higher. Up 3. And I know that I have to connect up from here to here to here, and I got to try to make the best circle I can. So as I do this, right, certainly not doing it perfectly, and in fact, have an eraser handy as you're doing these, right? It's definitely easy to make some mistakes for sure. Okay, and so there's my, yeah, see, I still kind of want a little more curvature there, so I'm gonna, there we go, that looks a little bit better. In the process, I accidentally erased this thing that's in the background. All right, so there's the top of that circle, and then, you know, in the XZ plane, that's when y equals 0, but that's kind of boring. That's going to be the same thing we got the last time, but it involves x and z. So z squared equals 9 minus x squared, so z squared plus x squared is equal to 9, but it's only the upper half once again. Okay, so now we're still connecting up here, but now I'm making it in the XZ plane. So this is gonna do something like that maybe. and then it's going to kind of drop back, and I'll try to maybe use a dashed line to indicate that it's hidden. And then this is where it's nice to, definitely do things with pencil if you can, because I want to indicate things that are not visible, right? So it's kind of customary to maybe make it dashed in the background when you can't quite see in reality what's going on there. And so, maybe make this kind of dashed instead. All right. But now you can see, right? You can see, what is this? This is the top half of a sphere after sketching out the traces. All right, so, and it's not perfect. I didn't do a perfect job of graphing this thing by any stretch of the imagination. So it's great to use technology to kind of confirm what you think you're seeing. And so in this particular case, I just change this, and in this particular grapher, to do square roots, you just go SQRT, and then in parentheses, I type what I want, 9 minus x squared minus y squared. And you might notice that things look a little bit funny. You might say, that doesn't look like what we just graphed. Okay, well, there's a couple reasons for that. One is, well, I should say the main one is, the way this is defaulted to set up is that it's going to take the function you give it, and then it's going to decide what z-scale it wants. But what we really would like is for the z-scale and the x and the y scale to all be the same. So I'm going to go change my bounds from auto to fixed. And now they all go from -5 to 5, and now it looks in proportion. So now that actually looks like a sphere. And again, you've got this kind of cutoff, as it gets steeper and steeper, the accuracy gets a little bit less, but that's okay. That we can still see that what we're getting there is the upper half of the sphere. All right, so here we're going to take a look at another example where you can use traces to understand what this thing looks like. The first thing to note here is that x is missing, right? And remember, when you have a variable missing, that doesn't mean that that x always equals 0 or anything like that. What it means is really that the graph looks the same for all x. So what that means is all we have to do then is let's go ahead and graph in the YZ plane. Okay, we'll write that down here. So we'll graph the trace in the YZ plane, and that trace will work for all x, right? So not just for x equals 0, right? The YZ plane is where x equals 0, but it'll work for all x. Okay, so what does this thing look like? All right, well, here's where we're going to have to kind of dig in our past a little bit. Okay, you might have to sit and think for a minute about what this thing is. So actually think about it for a minute, but here's what I'm going to remind you of. X squared over a squared minus y squared over b squared equals 1. That, in just 2 dimensions, remember, is the hyperbola where that's -a and that's a. And then you can also flip it around. Y squared over a squared minus x squared over b squared equals 1. That one, oops, That one similarly is a hyperbola, but because y is positive and x is negative, it's one of those where it opens up and down. Okay, so that's, that's something you've done. Probably not the thing that's just on the tip of your brain, but here's what it does tell us. In this case, we know that this is a hyperbola. Okay, but because we know it's a two-dimensional object and it is going to look the same no matter what the x is, we're going to take that hyperbola, and instead of saying it's a hyperbola, we're going to say it's a hyperbolic sheet. Okay, and we notice that the a is equal to, well, a squared equals 9, so a equals 3. So here's what this tells me. The positive one is the z, the negative's the y. So that means up here, okay, forget about 3 dimensions for a second. I'm going to sketch this one where I go up 3 in the z, and I go down 3 in the z, and I make my hyperbola. Okay? And as I do this, I'm just going to, I'm not going to probably make it as accurate as it really ought to be, right? But there it is, okay? And then it's also I'm gonna just go straight down here. I'm gonna kind of make these parallel, right, to do my best to make it look right. Okay, and so there's my hyperbola in the YZ plane. Okay, now I want to indicate though that this is not just a hyperbola, but it's a hyperbolic sheet, right? Because it's the same graph throughout all the x's. So I'm going to go way back here. I'm going to go back 1, 2, 3, 4. I guess we'll go back 4. And so what I want to do is I want to go up this same distance 3, this same distance, but I want to do it parallel to the z-axis. I'm going to go just try to eyeball about that same distance, right? And so then we can connect that with that. And then it's the same thing right here, okay? So what did I do? You can kind of line this up. It's about 3 back from the y-axis, and then up that far. So I'm going to go 3 back this way. 1, 2, 3. I'm just eyeballing it, and then I'm going to go up about that same height. So that's going to put me right about there. And then here, right, I don't know, that's about that distance back from 0. So about that same distance back from 0, but then straight up parallel to that x-axis. And I'm kind of running into my stuff there. But then this will allow me to try to give a sense for the fact that this thing is a sheet. Okay, and then what I can do is I can connect these lines or these points up that I've just made. Okay, and so now you can kind of see how it is that this sheet's forming, and so then you can maybe even kind of connect this up here to kind of give that thing some real, right? And so now you can see the side of that sheet, right? As you can kind of follow with your eye where this thing would connect up and make an edge in terms of your perspective on it. And then we can do the same thing down here, right? So I can go back 3, so I follow this same parallel line, okay? And I went down that far. Now I'm going to go down that same length there. All right, and then I'm going to this one here. So I went then down even further, but then I was quite a bit farther this way, And so understand what I'm doing. I'm trying to parallel that x-axis. So very lightly I'm going to sketch that in there. Parallel that x-axis, okay? But then from this point I went, you know, over this much and down that much. So I'm going to try to go over that much and down that much again. From this point I went over that much and down that much. So I want to kind of try to match that again. All right, it doesn't have to be perfect, but you're trying to kind of preserve the relationship that these points have with one another is really what your goal is. Okay, and I think here we didn't do too bad of a job. Okay, I can definitely see that sheet, right? So, and again, just to be clear, because some of this I'm kind of mumbling to myself, so I'm sorry. You know, I went over about this much and up about that much from that point to that point. So I should go over about that much and up about that same amount going from that point to that point. See how we have that that same relationship amongst the points happening, and that's what preserves the accuracy of the graph as we're trying to create it. All right, so there's a chart in your text that gives you some common types of surfaces that come up, and the type of equation that you're going to see when you do that. So you have ellipsoids. So ellipsoids are where you have x squared plus y squared, or x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. Now this should remind you of just the plain old ellipse. So remember that in your pre-calculus days, a two-dimensional ellipse would be one where you go out a and negative a and then down b and up b, and that forms your ellipse. Okay, and so not surprisingly, an ellipsoid is when you just add a c squared over c squared term. All right, here we have cones. If you ever have z squared equals x squared plus y squared with constants on the bottom, that's going to form cones. An elliptic paraboloid, okay? An elliptic paraboloid makes ellipses at various z values that you might be looking at. But then when you look at cross sections in the xz or the yz plane, they make parabolas, okay, when you look at traces. And then a hyperboloid of one sheet is one that kind of looks like the ellipse, except for one of them is a minus sign. And then a hyperbolic paraboloid, this is a cool one. This one is called a saddle. And when we get into Calc 4, saddles are going to be pretty important things in our study. And then finally, a hyperboloid of two sheets. So the hyperboloid of one sheet happens when you have one of them being negative, and a hyperboloid of two sheets happens when you get two of those values being negative, or two of the variables being negative. All right, so one of the things that you may do in this section is take a surface that looks like this, you can't really make sense out of it, and then try to convince yourself that it is in fact one of these surfaces that you see up here. So these are called quadric surfaces, so it's asking me to identify the quadric surface. So I guess it's giving away the fact that it is one of them, but it's asking which one. All right, so what we understand here is that these that I showed you in this list from the text, these are all centered at the origin, right? All of them are taking off from the origin, is one way to say it. So you could have a quadric surface that is not taking off from the origin. And when that happens, you know that there's just been shifting that has occurred. So let me just throw one example out there. If I took this form of an equation and I said x minus 1 squared over 4 plus y plus 2 squared over 9 plus z minus 3 squared over 16 equals 1. That's still an ellipsoid. It's still an ellipsoid. It's just been shifted so that its center is now at 1, negative 2, 3. All right, so down here, the idea is we can make this look something like this, or maybe one of these other surfaces, if we complete the square for each of the variables. So let's make a comment of that. We'll complete the square for each variable. All right, so 9x squared, there's no other x terms, so I don't feel like I need to do anything with that. So let's now gather up the y's. So y squared plus 2y, I think that needs to have the square completed, so I'll put a little plus a blank there. But then we have minus 4z squared. There's nothing else besides the z squared. So that's going to equal 0 plus whatever I add here. But we know that the thing we should add in such a case is half of the middle term squared. So I put a 1 there, 1 there. So this is 9x squared plus y plus 1 squared minus 4z squared is equal to 1. And don't let yourself be thrown off by the fact that all of these are being divided by a squared and b squared, right? This still fits into the group because if you really wanted to, you could say that this is x squared over 1/9, right? That's the same as 9x squared plus y plus 1 squared over 1 minus z squared over 1/4. And then furthermore, you could say this is x squared over 1/3 squared, y plus 1 squared over 1 squared, and z squared over 1/2 squared equals 1. And so then there's your a squared, your b squared, and your c squared. Okay, so we look at that and we say, okay, well, which one of those is it? I look up here, and it looks like that is the hyperboloid of one sheet, because that's where we have two pluses and a minus, where all of them are squared, and then it's equal to 1. So we can identify this as hyperboloid of one sheet. All right, so let's go ahead and take one of these quadric surfaces and let's see if we can sketch it. This is going to be tough. I'll admit that right now. This is going to be tough to sketch. So I'm going to take it slow and understand that this is a really hard one we're going to do here. So first of all, let's see if we can tell what kind of surface it is. All of them are squared, equal to 1. We have 2 of them are positive and 1's negative. That sounds like the one we just finished with. That sounds like the hyperboloid of one sheet. So that's what we're looking to do there. Okay, so going back then, now hyperboloid of one sheet, one thing that might help us is if we start sketching some traces. Okay, so let's do the XY plane. I'm pretty sure you heard that one. Okay, so z equals 0. So here we go. We've got x squared over 25 plus y squared over 9. And then the z is gone, right? Is equal to 1. So we just reminded ourselves this is an ellipse, right? This is an ellipse. And it's an ellipse where your x goes out 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. and you go up 3, down 3. So that's what it looks like in the XY plane, but guess what? That's exactly what we can sketch here. Right, this goes out to 5, this goes up to 3. So I can go in my X, I can go out 1, 2, 3, 4, 5. I can go back 1, 2, 3, 4, 5. So I know it's crossing there and there. And then I do the same thing, 1, 2, 3, 4, 5, but this is only going out to 3. 1, 2, 3, 4, 5. Again, it's only going to 3. So what I can do, and again, I'm going to do this very as lightly as I can here. I'm just going to very lightly sketch this in, and then I'll kind of fill in later the parts I really want to emphasize. But I'm just sketching an ellipse best I can. This is all just in the XY plane. Okay, so there's my ellipse in the XY plane. Let's try a different one. Let's try the XZ plane. So that's where y equals 0. So this is x squared over 25 minus z squared equals 1. All right, and as we reminded ourselves about a couple examples ago, this is going to be a hyperbola. But it's a hyperbola where you are where your x-intercept, or where your intercept is with the variable that's positive, right? So this means I go out to 5 and I make a hyperbola. So I know that it's going to do something like that. Okay? And similarly, I can go down and know it's going to do something like that. Okay? And I kind of want these to be parallel, make a parallel line from this point where I stop to this point where I stop down here with the z-axis. And then I can do the same thing, but I'm going to kind of try to parallel the x-axis. Okay, so here I went up that much, over that much. So I'm going to try to go up that much, over that much as well. So this is going to be something like that. And I went down that much, over that much. So I'm going to try to go down that much, over that much, oops, over that much, to try my best to kind of preserve that shape on either end. And then I can do the same thing. Sorry, I need to clean this up a little bit. There we go. And then I need to do the same thing over on with the YZ plane. That's also just going to give me a hyperbola. So the YZ plane is going to be y squared over 9 minus z squared equals 1. So that means I'm going here out to 3 and coming out about there, and then something like that, and then coming out so that it's again parallel to the z-axis. Okay, now I know that what I need to do is connect these points up here that I've created. Let's just start with the top. Okay, these need to be connected up, and they need to be connected up in another ellipse, because when you change the z value, it's still an ellipse. So let me scroll, yeah, here in the xy plane. If the z is something besides 0, then all that's going to happen is you're going to end up with a number here, which you can move over to this side, and then you can just divide by that number. So it changes your a and b and everything, but it's still an ellipse. So what I'm going to do here is we're going to sketch out another ellipse that connects all these points on top where I ended. Okay. And so you can kind of see what's happening. I'm kind of looking down into this thing. And then I'm going to now connect up the places on bottom. Some of these places I'm not going to be able to see. They're going to be hidden. They're going to be hidden by the other parts of the structure. Okay, but some of them I can. Okay, so what I can do now is maybe clean up a little bit so I can see just a little bit better. So, you know, that kind of stuff, I don't need to really see that. In fact, I can't see any of this, right? That bottom part of that hyperbole, but I can see this one coming up. This one here, yeah, I can see all that. Okay, and I guess maybe I can't quite see that one. And then, yeah, there we go. All right, so then I can't really see that. Okay, so this is me looking at it, okay, and hopefully you can kind of see this, right? This is, you know, what would this kind of look like? I guess maybe like maybe a fancy napkin ring or something like that. Is kind of the way you might be able to describe this. All right, now I'm looking at this thing and I'm thinking, okay, did I really do this right? Okay, well again, let's use technology to help us out here and help us determine if we've really done this right. And as I'm looking at this, I think I'm a little inaccurate over here. I don't really like that very much, so that should kind of make its way. There we go. I think that's a little bit better. All right, so let's look at it using some technology though. Okay, so first of all, how do we do that? Let me go back. It's not set up nicely to use in that grapher that I've given you. So what you do is you solve for z. Okay, so we go ahead and we say let's move z squared over to the right. So it'll be x squared over 25 plus y squared over 9 equals 1 plus z squared. So x squared over 25 plus y squared over 9 minus 1 equals z squared. And then that's going to give us two equations, right? When we take the square root, we've got to remember that we've got to do plus or minus x squared over 25 plus y squared over 9 minus 1. Okay, so I'm going to put those two in to my grapher. All right, so put in the square root of x squared plus, over 25 plus y squared over 9 minus 1. And let's change that discretization, right, to 100. And then I think I also want to change my x and y bounds to go -10 to 10. Because remember that our x's went from -5 to 5, our x intercepts were -5 to 5. So I want to see more of this graph. Okay, but of course that's just the upper half, right? And so I'm going to go ahead and then add another one, which is the same thing, but a negative in front of the square root. And of course I want these to match up, so we'll go -10 to 10 and -10 to 10. And let's make the discretizations match. Okay, and of course you got this interruption in here where the grapher's not sure what to do with this stuff as it approaches infinite steepness. But you can see this is making sense, right? We saw this kind of action, right, on the graph that we created. If I look straight down on it, there's my ellipse that I get in the xy plane with the trace in that xy plane. And so again, let's just go back real quick, right? You know, we honestly didn't do a bad job. This is really hard to graph, and we did a pretty decent job of representing what it is that's going on here. Never mind the rectangular borders here. That's just because of where the grapher's cutting it off. So you can imagine, kind of maybe look more at the changes in colors, right? So that the border between blue and green here, there's that ellipse that's up here that we also graphed right up here.